Okay, I'm going to go ahead and start here. I think I have maybe a person or two live with me, but yeah, I don't have anybody local at the moment. But I'll just get started, and if some people come in, I might restart or go back over some things. Go ahead and check. Yeah, I think everything's working here. So yeah, like I said, if uh, I, I usually have some people in here when I get started. I tend to not have a real good chance to kind of monitor the chat or stuff, but if you are live, I will try and check the chat whenever I'm doing these live class sessions. So do feel free to ask questions or things if you can. So it might be a short session. I know we're at the spring break, but yeah, if you're watching this after the fact, just some reminders that we do have the assignment 3. Morning. Uh, yeah, moment. But yeah, I went ahead and started the session in case anybody's gonna watch after the fact, or I do have one person online at the moment. So,
I guess maybe no one came because somebody saw it. A lot of people are like, they get stuck. They have to drive it sort.
But yeah, I just went ahead and started. I'll have this recorded in case anybody's watching after the fact, or I know that people will be. I don't have one person on at the moment online too, so. But yeah, it might be a short session. But yeah, although I wasn't going to go over the kind of the regularization stuff. So we've gotten into things that's really for the assignment 4, starting on Tuesday. So that's the main thing. I'd at least cover 30 or 40 minutes, talk about regularization techniques and the difference between underfitting and overfitting. That's kind of a big part of the next assignment. So just wait for this to warm up here. Huh.
Yes.
All right. So yeah, but yeah, just a reminder. I mean, I'm still looking for the assignment 3. I was gonna throw that up real quickly, remind a couple things on that, but let me know if people have questions on this. I took a look. Most people accepted, but only maybe half of you all have done some work on it at this point that I was looking at. I made a commit or something. So most people, well, about half of the people have accepted, but haven't done any commits yet. So I expect there's still a lot of people working on this. So don't forget about the third assignment before you go on break. Uh, there was a couple of things on this. So for one, the I didn't give any stub functions. So you do have to actually create the function in here. Don't if you put in the Python documentation, so don't forget that. But the other thing, I think I did bring this up before, mention some of these things, but I'll just mention them again just to make certain. So you do end up having to actually modify these. So you have to actually uncomment some stuff. So once you've created your, for example, the add dummy feature, test add the add dummy feature function, you should uncomment this in order to run the tests against it. Not to mention also you need to do the import inside the notebook, add these once you got them in. So that's a little bit different from the previous assignments. Don't forget that, but we did change the workflow on those. So. Oh, another thing that I noticed, just kind of a hint for people, it turned out something had changed. in the way that the built-in test runner was working. So, as a reminder, since a lot of people are still seem to be working on this third assignment, I mean, you can run those same tests for each of the features. So you can run it from the command line. We've got some little make files created for doing most of the stuff for these assignments. So you can't always do a make unit tests if there's no other way to run these. So these run the same tests that are being run in the notebooks. And initially they should be running, but they'll all end up failing. Although, yeah, they're going to end up failing initially on this assignment because you don't have the thing existing yet. But you should be able to run these tests from the notebook, but it turns out, I guess something has changed. I'll have to try to fix this for the stuff in the future as well. So once if you don't see on the left-hand side that it's automatically found the test to run them, I do find that sometimes you do seem to need to open up a notebook and run the notebook inside of VS Code. But then the other thing is that this discovery of tests here might not be working until it looks like you need to add in a file inside of the sources called __init__.py. So this is like a special file name that in Python that indicates the directory is actually a collection of things that forms a Python module that can import one of these __init__. But yeah, I found out, I was trying to do this last, maybe it was like a week ago. I was trying to show people how to run these tests inside of VS Code so you could edit and run inside of there instead of having to use Jupyter notebooks from Jupyter Lab to run all the stuff. So if you just throw in an empty init file, that should clear up the errors. You'll see that it will actually discover the tests, and then you'll be able to run the test runner from here as well, which I usually find when I'm actually writing the function for the assignments, I'm testing things out. It's a nice workflow. So with this, you can just edit the function in VS Code and run your test right from there and see whether they're passing stuff. All right. Anyway, I mean that was one thing, and back to the actual assignment. So yeah, we did change the workflow a little bit. So you do have to actually uncomment stuff. So these are the same tests that I was talking about. These are run from cells. Also, don't forget that I mean there is quite a bit of stuff to be run in the notebook. So yeah, if you haven't finished the assignment yet, make certain these points. Yeah.
So when you do the make unit test, that one all of them or only one?
I think that when you run these from the terminal, it will stop when one fails. So, but yeah, I mean, it should work. So if you're doing the first one, it will do that one. It'll just stop on the first one that fails. So yeah, if you're working through them in sequence, you can't use it from there. That's one way that the test run is better because it actually runs them individually instead of kind of running them all at once. So even if you are working on this and have stuff failing before, you can continue working on stuff after, not in a particular sequence. So. But yeah, that's true. It probably stops on the first one usually. Yeah, like when I ran it, it tried to do the test add dummy feature and it didn't do any of the others. It would go past that if that was passing. So yeah, don't forget about the notebooks. There are a lot of tasks to do. Well, some tasks to do in the Assignment 3 notebook. Also, do make certain your notebooks are running and that you save it and push those up So I kind of mentioned that before, that some people weren't actually kind of paying attention to their notebooks and making them part of the commit. So just trying to be aware of that. It's another thing I want to do sometime in the future is modify the GitHub action so it actually not only runs the notebook. So remember that in these GitHub actions, running the tests, but it does some additional things besides the tests. It runs, for example, the notebook. So one of the things it does here is just whatever notebook is in the commit that it's running the GitHub actions on, it will get that notebook and it will run it, see if it runs all the cells cleanly from top to bottom. That's really kind of what all this is doing here. But there's no check in the auto grader that all the cells are filled out. I do look at that by hand. I mean, that's what part of the grading that I do. Actually open up the notebook and make sure you did all the notebook tasks and things. So. But yeah, sometime in the future, I need to also check that it maybe reruns that, but actually saves the version after you reran it, because some people actually fill that out but don't actually have the notebook run for the commit they made. So, okay, but yeah, so just be aware of the notebooks as well. So just a couple of things to look at, and let me know. I don't know if anybody had any questions. I think we kind of went briefly over the actual stuff you need to do. And again, I'm only going over this because I did check today, and quite a few people, most everybody's accepted, but quite a few people still look like they have the majority of the stuff to finish up here yet. So, but feel free, if you have questions on this, to email me or let me know right now about stuff. So, I think there's a lot of the stuff you have to do, like define the loss function. So basically create a predict function, and something that does both the loss and the gradients is task 3. So a lot of those are pretty similar to the stuff in the notebooks from the lectures and stuff. So we should have a lot of good hints if you've read through the notebooks or looked at Dr. Hin's lectures on this notation, but actually getting the functions to work as described here. And also the same for gradient descent. So there were some examples of doing a full batch and mini batch, but this is really a full batch gradient descent here, where we use your previous 2 functions to iterate some fixed number of times and update the weights to try and find the goal. Okay, and then, yeah, as you'll see at the end, when we talked about this week or the week before, we mostly just so that we can visualize stuff, we're always using a linear regression where there was just one feature. So we could plot it as the regular figure where the feature was trying to predict the target variable, the price of the house or something. But all this stuff that we talked about, the linear regression and logistic regression, and later on, any parameterized model tends to work this way, support vector machines, things like that. It expands to, naturally, directly, without any additional mechanisms, to multiple features. So, it's just, can't really visualize it anymore once you have 2 or more features. What the resulting linear model is for like a linear regression, but mathematically it works just fine to fit 2 parameters, 3 parameters, or any number of parameters. So the last part is just demonstrating that. So you really shouldn't have to do anything to get the last part to work. In fact, there's no tests for that. You just need to run it and confirm that it actually gets you a similar result as you would get with the, like scikit-learn regression on the multi-feature data. And kind of as another hint on this, that you probably won't get exactly the same number if you kept iterating more than whatever we tell you to. It was like 10 iterations or 100 iterations. I can't remember the default, but the fit should be, on the last one here, and maybe the one before this as well. When we just do the gradient descent one feature, it ought to be close to within a couple, 3-4 decimal places. And you could get closer just by continuing the gradient descent. So if you kept iterating, you would get more and more in agreement with what you'll probably get if you do when you do the linear regression using scikit-learn. So you shouldn't expect an exact match, but it should at least a couple of decimal places on all the parameters for this one and for the one that's for a fitting with a single parameter. Okay, I'll move on to some new stuff. There's a couple of things that I want to talk about. So yeah, just back to reminders. So I know we're after spring break. Don't forget the assignment 3, and also just because of the way the scheduling worked out, there is actually an assignment due on the Friday of the week when we're back from spring break. And we started talking about the polynomial regression stuff on Tuesday. So I'm not going to continue on stuff. So really kind of the stuff I talked on Tuesday is more relevant to the next assignment 4. And the stuff I'll talk about today is going to be mostly about regularization for the next 30 minutes or so. Both of those are kind of the big topics for this assignment. But be aware of that as well. We do have a 4th assignment due on that week when we come back. And we'll continue discussing it when we come back after spring break as well. Including also, we're going to talk a little bit about logistic regression that week. So moving to applying these sorts of parameterized models for doing classification. All right. So, just give me a moment. I'll go ahead and open up so I can get my notebooks again for my class. Any questions on one? Yeah, the kind of last thing we talked about, just to ramp up for the next one, so we started talking about this idea of underfitting versus overfitting. I might not have mentioned bias variance, so those are kind of more fancy names from the same concepts that we're talking about here. Yeah, I mean this is usually kind of what I have in mind when we're talking about whether a model is underfitting or overfitting or is just right, kind of Goldilocks right in the middle here. So you can always in machine learning you're always fighting overfitting. To repeat a little bit of the stuff we talked about on Tuesday here. That's kind of the in these parameterized models like this. That's always the thing you're trying to overcome, because it's easy to throw a large number of parameters. If you don't know what is the best sort of number of parameters the size of your model is, you can always just throw a large number of parameters at it, and if you're not careful, the model will overfit. It will fit not only the data, but perfectly fit itself to the noise that you have. I mean, that's bad because these kinds of models won't generalize well. That's really kind of what neural networks and deep learning do. I mean, a neural network or a deep network has millions or billions of parameters. Maybe not billions, but a large number of parameters, right? So, in at first glance, it would seem like familiar with deep networks that they're always going to have an overfitting problem. That's part of the thing that having large, big data actually kind of helps with. So these kinds of models, linear regression, logistic regression, were kind of more in the classical statistics realm. So when you're doing classical statistics, you usually don't have really big data sets. You'll have collections of an experiment where you maybe had 100 participants or 500 participants or something like that. And kind of in that realm, you really have to be much more careful about overfitting. But you can have the opposite problem too. If you're trying to fit a model that's inherently nonlinear and you're fitting a line to it, you're never going to end up with a really great model. So in this case, it's a little bit tough to see that, but our model is this model, the truth behind this data that we generated here. It really wasn't linear, although over the range that we were fitting it to, a little bit hard to see that. But you'll never be able to get quite as good a generalization from a linear model as you would from a degree 2 model. And that's some books, some people talk about this bias versus variance. This is about generalization. The bias part is the part that is due to underfitting. So it's due to wrong assumptions about the power, about the true nature of the data that you're trying to model. So high bias is kind of another term for your model is not powerful. And just to skip in, when we talk about the learning curves, or when we talked about the learning curves here, and we're going to talk about these more. Did I do this stuff here? Look at these learning curves here. I think I talked about them a little bit on Tuesday. And then variance is kind of the other end. So high variance models are things we're kind of talking about when we're overfitting, where your model is excessively sensitive to noise. So if it starts fitting those kinds of small variations, it's probably fitting noise, and it's not going to do well making predictions on data too high variance. You have an overfit model. This, maybe I didn't talk about these in detail on Tuesday. So a big part of the fourth assignment is to do learning curves like this, although we do them in a slightly different way. The same idea here on assignment 4. So here we're showing. These are exactly the same as we do on assignment 4 here. So yeah, I don't think I did explain these or talk about these. So what we're doing here is we're showing on this first one what a typical learning curve would look like for a underfit model. Okay, so where we have high bias here, some bias, since we're using a degree 1 fit. So what these learning curves do here and in our assignment is we start. So if we just look at the code here, we start by fitting a model. So we're passed in the X and Y, and we split that out into train and validation data. So 20% of the data we hold back for the validation for this learning curve. Okay. The train here, but what we do is we train a model first. So in this loop, the first time we train a model with just one data point. And then we train it 2, 3, 4, 5. But then we validate it. So the other line on the training curve is we validate it with the data that we didn't train with. The data that was held back in this split here. So what happens typically for, it's easiest maybe to understand this. It takes a little bit of time to run here because we're using a large degree polynomial here. So for underfitting, what you'll see typically on learning curves like this is you will see convergence. So what's happening is, eventually, once I've got enough points, the performance on the red one here is how the model does with the data it was trained with. Okay. So this was we're using the root mean squared error here for the loss function, right? And remember, the lower the loss, the better it is. But typically, pretty quickly here for an underfit model, you're getting about the same performance on the training as you do with the validation data. So you wouldn't think that you're overfitting, so you're doing about as well on data you haven't seen as you did on data you did see. Okay. But so the question though is, okay, is this a good model? Okay. So if we use a more powerful model, down here, okay, finally. So here we use the overfit model. So typically for an overfit model, you'll see something like this. So you'll see a large range where the performance on the data you trained with does really well on that. But when it tries to generalize to unseen data, performance showed that in fact we just clipped it because it was extremely bad for most of the range here. So a learning curve like this is typical of an overfit model. So if there's a large range here where the predictions on unseen data is really much, much worse than predictions on the data we trained with, and you should suspect that your model has the high variance. So it's overfit in most of the range. But there's some, so as we discussed on the assignment 4, if you haven't looked at it, there is some use to creating a model that overfits. So this gives you some information. This tells us, so if you look at the level of the loss function that it obtained on the overfit regime, it gets a bit below 0.1 here, right? Where if you compare that to the result we had before, it was more like 0.17, 0.18, okay, for both the loss for the data we trained with and also the unseen data that we're trying to validate. So that gap there tells you that I'm likely, if I get a good model that has both low variance and low bias, so it's either underfitting or overfitting, I should get a model that converges quicker, so it's it does fairly well with unseen data, but its level should be more like its overall level of the loss function, which for error should look more like this, the underfitting that we did with the training, right? So a good model should look more like the first one, but should be converging somewhere much lower than 0.17. 0.18 that we had for the underfit model, or hopefully. This is kind of idealized. In the real world, things are a lot messier. So when you have to do stuff like this to try to tell if you're underfitting or overfitting, it's always going to be a lot tougher for real data because other things can affect these kind of stuff. But this is the basic idea. So here was using a quadratic model. So something to the power of 2, which we know from this data set that is the kind of the best power of a model that we can use. Is that was actually what was used to generate this data that we're using to illustrate. So this is what you'll typically see. Again, you don't expect a gap, but you can't really tell whether, whether we're in the underfitting or we have a good model unless you've also looked at a model that's really over. So here we can suspect that this is more like a good model because it doesn't look like it has that large gap. So it's not really overfitting. So relatively quickly, performance on unseen data is about the same as performance on the data we train with, but the level that we converge at is much lower than the underfit. This is definitely better. We might want to try a slightly more powerful model, Q with power 3, power 4, to see how that affects that. But that's kind of the purpose of these learning curves here. And yeah, that's for the assignment 4, you'll be doing that for all the stuff that we do, creating these learning curves and kind of demonstrating underfitting, overfitting, using these. Yeah.
Just in case if we are overfitting or overfitting the model, how do we fix that?
To fix these or fight these, you first have to know or suspect what you're doing, whether you're underfitting or overfitting. So yeah, the general procedure is to start by first creating a model that does seem to converge, right? So you first find a model that's like this, and so when you first find that, where you don't have a big gap between the performance for generalizing versus the data that you train with, you know that the model can represent the data. Then you try and obviously make a much more powerful model than that. So find a model that looks like it's overfitting. So if you can find a model that's overfitting, using the same kind of thing, then you know that maybe the first one that you found that does look like it can solve the problem, it can generalize, but it might not be the best model possible. It might be. So then you try and use techniques like regularization or other things for a model that's overfit, maybe not quite as overfit as this one, but then to regularize it, to fight the overfitting, to see if you can get better performance than the first convergent model. So, and yeah, that's kind of, for this, when we're talking about polynomial regression, it's obvious the way to fight it is to find the right number of parameters, the right degree of the model to use. But for other kinds of, like neural networks and things, you don't have quite as simple of a variable that you could tweak. So in those, you want to use more like a regularization. We'll talk about it. But you get a similar kind of thing. So here, if we reduce from a 100-degree polynomial to a 10-degree polynomial, we're obviously reducing the power of the model. We can look at that and see whether that's still overfitting or seems to be doing better at generalizing. But let's look at the regularization notebook here. So the more general technique are these called regularization. So these have another way of making it so that it will naturally fight overfitting automatically for you instead of having to by hand sort of tweak the number of parameters or do other stuff. Yeah, and the most basic one, so the ridge regression, the first one, in the assignment 4, you're asked to do like a ridge and a lasso. regression. So these are common names for these types of regularization. In classical statistics, you'll hear them referred to as ridge regression or lasso regression. So so in this notebook here, all we're doing is adding in what's called a penalty, regularization penalty. So if you look at this, so we're using the same cost function, like the mean squared error that we did before, but to that we, in addition, add in this additional term here. So all this does is, by adding this in, the sum of the squares of, remember, the theta are the parameters. So if those are 0, so if all the theta parameters were 0, this term would be 0. But if theta is really big, remember, those are the values that we multiply times a feature and sum up together to get our prediction. So if your parameters are really big, this term is going to be big. And remember, the goal is to reduce the cost here. Right? So by adding this in, this has the effect of trying to push these towards 0, make these as small as possible. Okay? And there's another term in here, this alpha. So you can tweak how important the regularization is, the square of the terms is. Again, if alpha is 0, it just goes away. We're just doing regular regression without any regularization. You make alpha really big, it doesn't matter how good your model is doing according to the mean squared error. It will be more important to get those to be 0 or as close to 0 if you make alpha too big. And you can tweak that anywhere in between. Rerun everything here on this notebook. So I just, in mathematicians will usually call this L2 normalization. So our textbook probably refers to this in 2 different ways here. So you can also do a similar idea. Remember, we talked about the mean squared error or the mean absolute error. So these regularizations, you can have the same kind of idea. You can just sum up the squares of the values of the parameters, add that to your cost function. Or the last regression is just summing up the absolute values of the things. Right? And you get a similar kind of regularization effect, although they have different properties. So we'll look at the one where we take the square. It's the L2 norm. Before I look at kind of the effect of this, so you might ask, so why does that have an effect? Or what effect does that have, putting in this regularization term? The idea is that if you're overfitting, if you allow these parameters to be as large as you want, that leads to being able to easily, go back to the first figure we have here. So by not constraining the size, if I have hundreds of parameters and not constrain the size of them, it makes it so I can have very large values for like the the x1 to the 100 term here. So we're using a degree 100 polynomial here. So that allows you to get really large changes here in order to wiggle around here and fit all the data. So if you constrain those to be really small or 0, if that's part of your cost function, you're going to inhibit or discourage this from making really big changes here in predictions. So if you keep those close to 0, even if you have a large number of parameters, they're not doing much. So they'll be less likely make large changes and wiggle around here to fit in extraneous noise that you don't really want to get as part of your model. So yeah, I don't know if that helped, but that's intuitively kind of what's happening here. So this fight's overfitting by trying to keep this so those are as small as possible, while at the same time they'll also keep into account that we're doing the same thing we talked about, trying to reduce the actual error, the average of the error term between our model and the actual data points that we're fitting to. So in practical terms, if you don't quite follow that explanation, let's look at the effect that it has here. So we're using the ridge regression here, where we use 3 different values of alpha. And I should point out, so we're using a model that has a degree 25. So we're doing a polynomial regression. The true model is still quadratic, but we're trying to fit a degree 25 polynomial. And by the way, here's some examples of using one of those pipelines from scikit-learn. You are supposed to use pipelines the same way to make it easier for your assignment 4. So all this does is at first, when we do a fit, it will first be expecting a single feature here. And it will do the polynomial features so that we now have all the features up to degree 25. And then it will fit a ridge regression, which is using that normalization term, which is the square of the parameters with a particular alpha. So again, if we have alpha 0, we're not doing any regularization. So we're really just doing the linear regression. And so the result of that is the blue here. So similar to what we showed on the previous notebook, we're overfit. We don't do any regularization, it wiggles around a lot, and if we measure how well this generalizes, it wouldn't do well. If we use a lot of alpha, so if alpha is 100, that's the green one here, the effect is it tends to make all the parameters 0 except for the bias term. So you get something pretty close to like a line if alpha is too high. So you'll get it to an underfitting. If you do too much regularization, you're mostly kind of ignoring the data here, and you end up with just like a linear model for the most part. And so if you tweak alpha somewhere between those, you will get something similar. So here, what the dash is the true function. So that was the true quadratic function. And again, in the real world, you wouldn't know what that is. You can see how close different values of alpha have to getting it to match up with the actual degree 2 polynomial that generated this data. And you can also see that the effect of that in the weights. So if we look at the actual coefficients, so in this case, the 3 that we have here, we're using the alpha of 0, the really large alpha, and then the alpha that was just right. Okay? So the effect isn't quite as easy to see on this one. So when the alpha is really large, you expect all these values, all the coefficients to be pushed down to close to 0, which you can kind of see that. So most of them are 0.01, 0.00 something. Except for so this regularization doesn't affect the coefficient, so it ends up being about the average of the y values for all of these. So it mostly affects. So if we don't have any regularization, notice how big the beta parameters are here. Right? That's allowing function, the predictions to make really large changes. With a right amount of alpha or too much alpha, you get much closer to 0. That's the overall effect. So using the absolute value, like the mean absolute error, we can also use the absolute value, the sum of the absolute values of these, because again, the larger these are, the bigger the penalty we want. So this is known as the L1 norm. I don't know why I didn't mention it, the L2 norm previously. This is kind of more from mathematics, but from classical statistics, they call this lasso regression. I don't know why. I think this is like an acronym or something. So you'll see a similar. One kind of nice thing about this in terms of polynomial regression is this has the effect when you use the absolute value instead of the square for this penalty or this norm term. It has the effect of driving things actually to zero that aren't useful. And that's very, very much what we kind of want for this polynomial regression, because if we only have a square model, we would like the cube and the fourth power and the fifth power to actually all be zero and only use the power of the one and the square power terms. Even though we start out with a model with a degree 25 polynomial, we would like everything that's not actually good for making predictions to be driven to zero. The stuff that is working to give good predictions is not good. And this kind of has that effect. We use the absolute values of the square. So again, you can see that. So you get a similar thing, although it actually, if alpha is too large, so here alpha 1.0 is actually too large. It's a little bit different from before. We needed a much smaller range. So when you get 1, though, you end up with an actual line, as we'll see. And alpha of 0 is still, actually, the observant student will notice, I'm not certain why. If you set alpha to exactly 0, this has problems that I don't know why. So you can't make it exactly 0. But if you make it even really small, so the smallest that we use here was, where is it? We just used 0.01. Oh no, yeah, we did use 0, but we got some warnings. So something. So the reason why I'm kind of pausing on that is I would expect this to look the same as when we used alpha 0 for the ridge regression, but obviously it's not quite doing exactly the same thing because it's not quite as overfit, and also it doesn't converge when we do that. But yeah, I don't know exactly the true reason. It's doing a little bit more than having just a simple sum of the absolute values. It must be doing something else. But we get the same kind of effect, though. It's still kind of overfit, but the one with kind of a good amount of alpha is getting close to the true function. We get too much alpha 1 here. We end up with a underfit model. And again, if you look at the parameters, this is what I meant by that. So the one which had kind of about the right amount, notice that we end up with only the x to 0, x to 1, and the x squared term. Everything else pretty much got driven to 0 using this L1. And if it's too large, we end up losing the terms that are useful for this polynomial model. So everything's 0. So this is really just a line that goes to 3.2 on the y-intercept here, since all the terms, x1 to x to the 25 power are all 0 here, basically. And we just have a few more minutes. Elastic net. I don't remember if I asked you to do that on the 4th assignment. It's really just, I don't know if in practice how many people find elastic net useful. It's really just a combination of both the ridge and the lasso, or the L1 and the L2 norm. So we have a term both for the absolute value and the square. although there's also an alpha, but there's this R term in order to, so if R is 1, we're actually only using the last of the absolute value. If R is 0, that goes away, and we're actually only using the, so that reduces to the ridge regression of the L2. So by tweaking R, you can get a combination of the two at the same time. That's where all the elastic regression is. And speaking of, so like if you take my neural networks course in the summer, I mean, you can use exactly the same type of regularization. A neural network is really just a set of layers that are doing like a linear logistic regression in multiple steps. So you can use L1 or L2 regularization. Another common thing for neural networks, though, is to just do early stopping. So if you're fitting a model, this is again a type of learning curve, a little bit different from the ones we looked at before. So this is doing the same thing like you're doing in your assignment right now, like a gradient descent, where we train for some number of epochs. If you are overfitting, what you'll normally see if you're doing like a gradient descent or some sort of optimization is that the performance on the validation data that you're looking to see how you're generalizing will improve for some portion of the time. But if you're going to start overfitting, at some point, the generalization will get worse. Will start getting worse and worse. Even though normally the performance on the data you're training with should always keep getting better and better, or less and less on your loss function, although it might level off to be about the same at some point. And that's expected. So if you have a model that's too powerful, if you're doing a normal gradient descent optimization, for a while, it'll take a while before it's actually overfit, before our parameters become too big and it's starting to fit the noise we have. But eventually you'll hit that point if your model is too powerful. At that point, further iterations of your optimization will reduce the loss by fitting to the noise. So another common way to fight overfitting is to just plot out a learning curve like this, determine the point where our validation, our generalization performance starts getting worse, and then train models just up to that point. So this is doing a similar kind of fighting of overfitting. And this is applicable to a lot of parameterized models. Yep.
I have a question.
Sure.
For the defense sequence net, it is in the for defense sequence, do we still keep the default that we achieved from the
for sequence lengths? For what do you mean by sequence length? The
like the amount of the for example, for sequence length, I will not take like 5 and take that and those data and put it to the model.
right.
So in that case, we might need to we should always opting for this sorry, let me be clear. So for sequence length 5 and sequence length 10.
Right. Are you talking about like what we were doing? So we are doing slightly different things. So is this what you're referring to? Like here, we're not doing a gradient descent, and we're calling both of these learning curves. But here we took like 200. We only trained the model with 200 points and tried to look at the performance on data that we had trained. But then we selected 300 points, 400 points. Is that what you mean by
yes.
Yeah, so a similar thing happens for both of these. The difference, I mean, these are both considered learning curves. The difference here, I mean, we might have split the data into training and test data. But when we do a learning curve like this, we're doing kind of the same thing that we did before. So if we split it into training and test data, we're going to fit the model to all the training data, but when we generate this while we're doing like a gradient descent, we're generating this curve using that held back test data. Or like libraries like Keras or TensorFlow, you can specify when you do the fit that here's the data, give me the performance on validation data, and it will do that split for you. Right? So again, I don't know how. So whenever you do this optimization, these are doing pretty much the same kinds of thing. So a common thing that happens in TensorFlow or Keras is you just give it a set of data and you ask it to do a validation split for you, and it will return back for every epoch or whatever you ask it for. It will return back how well it performs on the data that it fit the model to, but also how well it generalized to some other data that it didn't use as part of it. So yeah, I don't know if that's exactly what you're asking about, but yeah, I mean this is common, right? So most libraries, as part of the scikit-learn doesn't do that. So scikit-learn, when you ask it to fit a model, it doesn't have options like I'm talking about here. So for scikit-learn, we kind of, I guess that's kind of one argument for why we do it like this on our assignment. In this case, is we have to get a similar thing, so we can't get into the optimization epochs. So instead, we just train it with increasingly larger amounts of data, and evaluate it on how it's done that data, but also evaluate on other data that it was used in order to see how it's doing on its generalization. So anyway, I mean, in both cases, the goal really though is we need to see the difference. We need to get a feel for whether it's generalized, whether it's overfitting. All right. Just check. Yep. So yeah, that's it for today. I'll let you guys go. After the break. I mean, yeah. So everybody watching this, do get the assignment 3 done, but then take a little bit of time. Spring break. Spring break. We give her a rest.
So for exam, we're gonna have the like examples on March 15th. That's the day next time.
Yes. So yeah. Thank you. So. No, I mean I might have had the dates. We're going to do one more full week talking about logistic regression in assignment 4, and then that week will all be for the exam. So it would be the 23rd. I'll probably have it about